Before starting this next lesson, try the warm-up. This warm-up involves reaching back to the previous unit about exponential functions. See if you can figure this out. A town has a current population of 5,000. If it grows by 4% annually, what will be the population in 25 years? So reach back to your memories to exponential functions so that you can make an equation, and then use what you know from this unit on logarithms to solve. See how you do. So pause the video, try it, and then come back and we'll take it up. So if you'll recall from the unit on exponential functions, we always write them in this format. So the first number here, the coefficient in front, that's your initial value. So in this case, it's the current population of 5,000. So our starting population is 5,000. And then the base of the power is your growth or decay rate. So this is growing by 4% each year. So if it's growing by 4% each year, we're going 4% higher than 100%. So 1.04, it's growing by 4%. It's that 100% plus 4 more percent. Okay, so 1.04, not just 0.04. And then the exponent, in this case, is the number of years. So I made it 25, because we're looking at the population after 25 years. Now, just for good communication, I defined my variable p to represent the population. Okay, now I just plug this into my calculator. 5,000 multiplied by 1.04 to the exponent 25. If you're not comfortable with your calculator, you might want to do this in steps. So you can do 1.04 to the exponent 25, hit equals, and then multiply your answer by 5,000. Any way you do it, you should get approximately 13,329 as the population in 25 years. So that was an application of exponential functions, but remember, logarithmic functions are the inverse of exponents. So we're going to look at applications of logarithmic functions. So I have 3 examples that I'm going to work through. And the whole goal here is so that you're able to extend your knowledge of solving exponential and logarithmic equations to real-world situations. And also, you should be able to reflect on the reasonableness of your answer. So I'm not going to directly teach this in this lesson, but it's always something you should be aware of. Look at the context of the question, and when you get an answer, ask yourself, does it make sense? If it doesn't make any sense at all, then chances are you didn't do something right, and you should go back and check your work. Now, I'm just reminding you here of some formulas that we went over in the exponential functions unit. So we have mathematical modeling, compound interest, half-life. These are all different ways of writing equations to model growth or decay. So this is just the general form for any mathematical modeling. A is your your initial value, B is your growth rate or your decay rate, depending on what you're measuring. If it's growth, it's going to be a number greater than 1. If it's decay, it's going to be a number less than 1. X is just whatever your independent variable is, most often time or something like that. Okay, so all of your equations are going to follow this format. Now, this is a specific application, is compound interest. When we're talking about money, the value of the money grows. But notice this, it's following the same format. You start with your initial value, which is the present value of your money. This is your growth rate. So 1 plus the interest rate per compounding period, that's the rate that it's growing each compounding period. And X is your independent variable. Well, the independent variable when we're talking about compound interest is the number of compounding periods. And we also have half-life. So we have the starting amount, the decay rate, which if we're talking about half-life, it's decaying to half, so 0.5 in half-life. And then your exponent, x divided by t. So x is just the amount of time, t is the half-life length, okay? But just keep in mind, we're always following this format, a times b to the exponent x. So the first example is a financial question. Bob has decided to invest $5,000 in an account that earns 8% per annum, that means per year, compounded quarterly. Okay, so this is a compound interest question. We're starting with $5,000. It's growing by 8% per year, but it's compounded quarterly, so we have to make an adjustment to our interest rate per compounding period. Write an equation to model Bob's investment. I'm going to start with our compound interest formula, and I'm going to plug in the numbers that I know. I know that P is $5,000, that's what he's starting with. Now I is the interest rate per compounding period. So it's not 8%, we have to divide that by 4 because it's compounded quarterly. So 8% divided by 4, well that's 2%. So 1 plus 0.02. Or I can simplify that and just say 1.02. Now the exponent, n, it's not the number of years, it's the number of compounding periods. Now, in the question, I haven't been told how long, so I just have to leave it as an n for now. Now, part B, how long will it take for his investment to triple? Okay, so we know the investment is tripling. So if he's starting with $5,000, triple means you're multiplying by 3. So that's $15,000 it's going to end up being. So I can plug that in for A, my future value. Okay, so now I have an equation. I don't know the value of n, but that's what I'm trying to figure out because it says how long. That's what this measures. So now I just have to solve. Well, simplest thing right now is to divide both sides by 5,000. So now I end up with an equation 3 equals 1.02 to the exponent n. So now I have an equation in exponential form. And like in the last lesson, when I showed you how to solve these logarithmic equations, we can do the same thing here. So I'm going to take the log of both sides, use that exponent rule for logarithms. So I bring the exponent of n to be the coefficient. So now I have log of 3 equals n times log of 1.02. To solve for n, divide both sides by log of 1.02. So I end up with n is equal to log of 3 divided by log of 1.02. Do that in my calculator, and I get 55.4781 approximately. Okay, so now we go back to the question, how long will it take for his investment to triple? A lot of people will stop here and they'll say, oh, it's going to take 55 years. But remember what n represents. N is the number of compounding periods because we're talking about compound interest. So in order to get the number of years, we have to divide this by 4, which ends up being about 13.9. So I'm going to say it will take approximately 14 years for his investment to triple. Okay, so we have an equation, an exponential form. We take the log of both sides, and then we can simplify and solve. That's going to be the common theme for the next couple examples. Okay, Brenda has a pet ant farm. She started the colony with 25 ants and has measured the growth rate to be 48% per year. So we're going to write an equation to model the ant population. Then we're going to use that equation to figure out how many years will it take to have 1,000 ants. Okay, so this is a population question. So I'm going to use the variable p to represent population. My starting population is 25. We're starting with 25 ants. Now every year it grows by 48%. So we're going to say the growth rate is 1.48. And then my independent variable, I'll just leave it as an x just for simplicity. That represents the number of years. So it's always the same format: initial value, growth or decay rate, independent variable. How many years, so we're solving for x, will it take to have 1,000 ants? So I know P is 1,000. So I can write my equation. Now I'll have to divide both sides by 25. 1,000 divided by 25 is 40. The 25s cancel each other out, so I'm left with 1.48 to the exponent x. So I have 40 equals 1.48 to the exponent x. Now remember my strategy here. I need to take the log of both sides, move that exponent down, so I end up with log 40 equals x times log 1.48. I want to solve for x, so I need to divide both sides by log of 1.48. And that leaves me with log 40 divided by log 1.48 equals x. So I plug that into my calculator. Log 40 divided by log of 1.48. It's approximately 9.4. So I can say, therefore, it will take about 9.5 years to have 1,000 ants. So I did the same strategy as the first example. Once I have my equation and I plug in what I know, if I want to solve for the exponent, simplify what you can, take the log of both sides, and then you just divide both sides by the logarithm that's attached to the x. Okay, we're going to do a similar thing in the next and final example. Roberta has 150 grams of radioactive zoomanium in her closet. Just so you know, this is a made-up element. It has a half-life of 80 days. So just remember what half-life means. It means for this sample, it's going to take 80 days for it to decrease to half the amount. And after another 80 days, it will be another half of the amount. So every 80 days, there's half the amount of what there was at the start of the previous 80 days. So write an equation and then figure out how long it's going to take to get 1 gram. So we're modeling the mass of zoomanium. So I'm going to use an m to represent the mass. The mass is equal to, well, what's the initial value? It starts with 150 grams. Okay, now the base of my power is the growth or decay rate. Well, it's talking about half-life. So it's going to take 80 days to reach half the amount. So my decay rate is 0.5. I'm reaching half the amount. Now we have to be careful with the exponent. Okay, so we're told that the half-life is 80 days. So that doesn't mean that the exponent is 80. But it does mean that the value in the exponent is going to be measured in days. So we're going to have d for days. But then we have to make an adjustment because it's not every day that it's reaching half the amount. It's every 80 days. So for example, if we left the sample for 1 day, it's going 1/80th of the full half-life. So we have to divide the number of days by 80. And that's true anytime you have a half-life question, your exponent has to be divided by the half-life. So if your half-life is given in days, then the numerator in your exponent is the number of days. If your half-life is given in years, then that would represent the number of years, etc. Okay, so we have an equation. How long will it take for there to be 1 gram left? So the mass is 1 gram. And now we can solve it the same way we did before. I'm going to challenge you here to try the rest of this question on your own. So pause the video, try the math, and see if you get the same as me. Long story short, it's about 578 days. So you can compare your solution with mine. If you made a mistake somewhere, hopefully you can find it. I'll quickly go through what I did. I started by just dividing both sides by 150. So I had 1 over 150 equals 0.5 to the exponent d over 80. Took the log of both sides, moved the exponent down, so then I ended up with this line. To get d by itself, I had to divide both sides by log of 0.5 and multiply both sides by 80. So I ended up with d is equal to 80 multiplied by the log of 1/150th divided by the log of 0.5. If you do that correctly in your calculator, you should get about 578 days. Okay, so the gist of all these questions was that you start with an equation, you can solve for the exponent by taking the log of both sides and doing the math for solving equations that we learned in the previous lesson. So try the practice questions. If you run into any difficulties, let me know and I'll do my best to help.